Hey everyone, this is RaptorChatter here with the first part of the year in review that's organized by Edge every year among paleo YouTubers. With all that said, I'm going to be looking at some of the biggest finds from January, so let's get started. To get started, we're going to be looking at something that could be very important for future research, and that's the first potential fossils of choanoflagellates, which are actually really closely related to metazoa, which is animals, just period end. All animals are metazoans, meaning this is potentially our sister group, and again, the first fossils of them that we've ever found. Choanoflagellates are called this because they have a flagellum. It's this long tail kind of thing that they flop around and are able to move through the water with that. And oftentimes they're also colonial and will live together. These fossils that are found using scanning electron microscopes were actually shown to have potentially the flagellum and some of the connective tissues that would have connected the different cells of the colony. With these being the first fossils from choanoflagellates, it does mean at least hopefully we can start using some of these methods to look for them elsewhere and potentially really understand when choanoflagellates started to evolve, because that would also mean potentially the evolution of animals as a whole. Jumping into more famous paleontological discussions though, we also had a paper that was saying, hey, Tyrannosaurus could have been as smart or at least had as many neurons as a baboon, which would have been a lot. Now this paper was criticized at the time because it was written by a neuroscientist, not a paleontologist, meaning that there are some gaps in the differences of what they're specialized in. And yes, they are very smart at looking at brains, but fossils are a lot harder to try and make these inferences from. And so while it is a really interesting study, I think we're going to need a little bit more work before we really understand how much this is the case and what kind of intelligence animals like Tyrannosaurus rex had. I also have an entire video on that if you're interested, but that's a much longer story. Finish this first. Looking at other dinosaurs, we're going to be actually looking at a very early bird, Creus XA, which is really interesting because when we look at its skull isn't actually that bird-like. And that's because it's a largely akinetic skull, meaning the bones don't really move relative to one another that much. Meanwhile, when you look at modern birds, especially things like parrots, you can see they have a very kinetic skull. The bones do move a whole lot relative to one another. In general, most dinosaurs had akinetic skulls, and it's just the birds that really changed this. This fossil is interesting though because it still has a lot of other bird-like features, such as a pygostyle, which would have let it make a fan of feathers at the end of its tail, as opposed to having a deep V in it like we expect to find in many kinds of dromaeosaurs. This means that the evolution of bird skulls is actually totally separate from their ability to fly, because from what we know of Creus, it definitely could fly. Its hands were built for flight. They were built and looked like modern bird wings, at least mostly. This means that this isn't something we can just go, oh cool, they evolved this all and their specialized skulls just because of flight. No, it was a later pressure that actually really led to this kind of adaptation, and hopefully with more fossils we'll be able to understand better how bird skulls actually took their shape. Speaking of the hands of dinosaurs, we're going to be jumping into the Megaraptorians, which are one of the worst known groups of dinosaurs, but had very large hands. And it's suggested that this was probably for capturing prey, and potentially they didn't have as large and bulky of heads as many other theropods, especially large theropods like the Tyrannosaurs or the Giganotosaurs. However, this paper is actually looking at the musculature in those hands to see how good they would have been at actually catching something. The researchers mapped out where different muscles would have attached based on the arm fossils we do have of many different Megaraptorians, and you can see that with the different muscles being labeled in this image. These muscles aren't really that different from any other theropod's arms, though they're just larger. This suggests that it was already built in for theropods to have these kinds of grappling hands, and the Megaraptorians just took it to an extra extreme. That's especially true when you look at not necessarily the muscles, but the tendons, where potentially they had a greater ability to flex their hands and move them in different directions when wrangling prey. And apparently that is what those big meaty claws were used for. Despite their name, Megaraptorians aren't actually that closely related to the raptor dinosaurs or the dromaeosaurs. However, they also had very similar adaptations, except in raptor dinosaurs, it was on the feet with their large sickle claws. And a paper also looked at modern-day birds to try and understand how they might have used those claws. And that's because the red-legged Seriema actually was able to use its claws to hold down prey and then be able to dispatch it using its beak, or potentially by slamming it into the ground the way modern-day Seriemas do, which is very intensive. This suggests that, unlike Jurassic Park, where they talk about, oh, this claw is used to cut animals open, it's really not that likely that that's what it was for. Instead, it's more likely that it aligns with the raptor prey restraint hypothesis, which is essentially that, no, this claw is there so that it could use its feet to control its prey, and then again, dispatch it using its head. It's not necessarily this big dramatic slicing weapon the way that Jurassic Park suggests. Staying with Archosaurs, but this time jumping to the pterosaurs, there was a new ctenochasmatid named, and it's been called Balaenorhynchus mauseri. And it's actually really interesting because it seems like it was very, very well adapted to filter feeding. There's a few other pterosaurs that have been suggested to have been filter feeders. However, this one is taking that to a very large extreme, and potentially was actually able to just sit in a current and filter feed very small crustaceans or other plankton that would have been flowing along the current. And then it could essentially scoop that up, push out the water, and eat what was left. What I may think be a different alternative to this very passive hypothesis, though, is that it could have potentially been feeding more like a roseate spoonbill, which is much more active and walking around the water while it feeds. But we see this kind of thing in large birds today. It makes sense that pterosaurs could have filled a similar niche millions of years ago. On the subject of movement, we can look at the first archosaur, or at least the earliest known diverging archosaur, and that's Euparkeria. Euparkeria is known as the first archosaur because it's the first fossil that we've really found that had its legs straight down below its body, as opposed to sprawling out more like a lizard. It's even been suggested that Euparkeria could have ran on just 2 legs, but that hasn't really been quantitatively tested until this paper came out. And with all their math and many graphs showing the different ranges of motion in the different limbs, it seems like Euparkeria was actually probably quadrupedal and couldn't really run on 2 legs. Still though, that action and evolution of moving up and off the ground to facilitate a different type of movement served the archosaurs well, as the dinosaurs and the crocodilians would both evolve from this group. But there were other organisms also evolving around the Triassic, and some of them we still have today, including the Sicilians, or Gymnophonia. These are weird amphibians that mostly live underground and are kind of tube-like. Often they don't even have limbs, and sometimes they produce a mucus that their young eat. They're a weird group. But now we have the earliest known fossil of one coming from the Triassic of the Petrified Forest National Park. Fungus vermis gilmori is known from microfossil sites, and what that means is they took a whole bunch of mud from the park, sifted it through many different sizes of strainers, and then were able to look at that under a microscope and go, hey, that looks like a bone. Hey, that looks like another piece of a bone. That looks like another piece of a bone. And then very carefully glue those together so that you can see what kind of bone it would have been. And it does align with the Sicilians. This is really interesting, and it actually does support some differences in what we potentially thought about their evolution. Because amphibian evolution is really hard to know. We have very large amphibians in the fossil record, or at least amphibian relatives, like the temnospondyls, and then suddenly we just get almost modern amphibians. That includes frogs and salamanders and some Sicilians. Because of some of the traits that are present on Fungus vermis's jawbones, it really does suggest that they actually came from one specific group of the temnospondyls, the Dicerophoids, and that from the Dicerophoids, all modern-day amphibian groups, the Sicilians, the amphibians, and the frogs, all evolved from. It's not like there was some separate group that was more ancestral in their evolution that the Sicilians split off from, and they just happened to persist in the modern day. It's also really important for understanding where Sicilians are today, because they basically live along the equator, and at this time in Arizona, that would have been the equator. So it seems like they evolved there and then basically stayed there. As for strange animals from slightly earlier, we have the Inoopterigids, which are very strange chimera relatives, which means they're related to sharks, but not sharks. Think of things like the ratfish as an example of a modern day one. However, this study was looking at their jaws to see how they likely fed. What they found is high-performance suction feeding. And by that it means essentially the way frogfish do today. They sit on the bottom and potentially just open their mouth very quickly, and that draws in a lot of water and the prey. Now, it's really hard to say for sure if the Inoopterigids actually sat along the bottom. However, their very, very strange fins, I think at least, do suggest that it would have been possible for them to do that. And then potentially they were just filling that niche along different reef systems. And unfortunately the Permian-Triassic extinction came and they went extinct because they are wild animals. I would have loved to see what one looked like in real life. Speaking of fossils, before the Permian-Triassic extinction, there is also a look at insect fossils. And this is really important because the Permian-Triassic extinction is the only mass extinction that significantly affected what kind of insects were around. And it was essentially just trying to go, hey, what kinds of groups of insects were around beforehand and afterwards? Genetic data has been able to show certain divergent times for different groups of insects. One such example is the wasps, which it's suggested diverged from the other insects back before the Permian-Triassic extinction. The question is just, were they actually wasps then, or were they just the precursors to wasps? And what the paper finds is probably not. And this tracks with a lot of groups. Essentially, the crown group didn't exist yet, but they had diverged from their relatives. When I say crown group, it's essentially the first ancestor with all of the traits we would associate with that later group, or essentially the modern animals that are related to it. What this means is the Paleozoic insect fossil record is still very important for understanding their modern diversity. However, when we want to understand the evolution towards modern day types of insects, we need to look after the Permian-Triassic extinction, especially with the start of things like angiosperms much later during the Cretaceous, where suddenly they burst into life and that opened up a lot of ecospace for different animals. And on the subject of arthropods, there was also a paper that looked at Wallicerops, which is a strange genus of trilobites with long tridents at their front, and it's been suggested these could have been used for many different things, including potentially foraging. However, one was found to have had a damaged trident. It actually turned into a fork, and a very poorly built fork at that. With the poorly built fork of this one individual of Wallicerops, it really suggests it wasn't used for feeding, because this thing was almost fully grown. It wasn't necessarily slowed down that much just because of a damaged trident. This makes it much more likely that this trident was actually being used for competition within its own species. Essentially, hey, we want to try and win over mates, we're going to fight about it. There's also some other fossils of other trilobites from the same area that could represent the other sex of the trilobites, but it's really hard to know that for sure. And finally, in human evolution, it's kind of a crapshoot sometimes. And by that I mean a lot of times when we look at our phylogenies, they don't line up the same way. Or sometimes there's the same genus that is actually placed on many different lines that aren't very close to one another and with other species in between. It means there needs to be a lot of revision of taxonomy for hominin evolution. And you'll hear more about some of this from Will later in one of the other months in reviews. However, this paper essentially went, hey, look, we've reanalyzed Australopithecus, and it actually does line up somewhat closer to some of the other hypotheses. Again, there's going to be a lot of work to try and get hominin evolution better understood. The taxonomy is just, it's terrible. However, this is a good step to start working on that, and hopefully we'll see some more progress on this further in the future.
Where's Rick?
I'm
Don't care. Where's Rick?
Hello dear viewers, Edge has invited me to be in this year's PaleoRewind. So let me tell you about the most interesting papers published this February. Also, Edge said make the video as you as possible, so...
But he runs into another predator that is waiting for him. The claws of the Tyrannosaurus pierce the youngster's body.
It's a total fabrication. Not this time. It never happened. This one was invented by a writer. It's an urban legend that never happened.
Functional space analyses reveal the function and evolution of the most bizarre theropod manual unguals. Chin et al. Did a morphological analysis of the claws of Alvarezsaurs and Ferosasaurus to see how well they would handle the stress of the following physical actions: piercing, scratch digging, and hook and pulling. For reference, they analyzed the claws of Guanlong and Allosaurus to represent more typical theropods, and compared the results to the claws of mammals with well understood ecology, namely a puma, a pangolin, a tamandua, and a ground sloth. Unsurprisingly, the typical theropod claws are rather unspecialized like those of the puma, and perform well at all three functions, although they are worse at digging than the other actions. The most basal Alvarezsaurs like Haplocyrus had grasping hands that were bad at digging, but once you get to more derived Alvarezsaurs with their stubby one-clawed arms, the digging capabilities get better. Mononychus in particular performs most similar to the pangolin, another indicator that like this mammal, Mononychus would have been a specialized insectivore breaking open termite mounds. Therizinosaurs turned out to be bad at scratch digging, with early Therizinosaurs like Alxasaurus being good at piercing and pulling, so they probably grasped tree branches, similar to how it is assumed for ground sloths. Well, that whole paper just confirmed things we already expected. What's the big deal? Oh, this is the performance of Therizinosaurus itself. And it turns out the long claws of Therizinosaurus suck at everything. Digging, pulling, piercing. All result in high stress levels that the claws wouldn't be able to bear. So unfortunately, Therizinosaurus probably didn't slap giant theropods with its claws. It probably couldn't even pull in tree branches for feeding like its earlier relatives did. Not that it needed that at its size and neck length. Even when you account for how much larger Ferosasaurus is than other Ferosaurs, its claws are disproportionately large. You hate to hear it, but those oversized claws were most likely used just for visual display. On the plus side, imagine how cool their mating dances must have looked like. Largest known fossil penguin provides insight into the early evolution of pheniciform body size and flipper anatomy. Xepka et al. Described giant New Zealand penguins from the late Paleocene Meraki Formation, which was deposited 55 to 59 million years ago, only 10 million years or even less after the KPG extinction event. One of these is the new species Kumimanu fordyceae. With how fragmentary fossil penguins are, it is difficult to estimate how tall they would have been, so a more reliable size estimate is measuring their arm or leg bones and use them as proxy to calculate their body mass. Based on its humerus, Kumimanu fordyceae is estimated to have weighed 159 kilograms, making it the largest penguin to have ever lived. Another new species from the same formation is Petradiptus stonehousei, and even that one was still larger than a modern emperor penguin. There are already many other species of giant penguins from the Paleocene and Eocene, but Kumimanu fordyceae is one of the earliest and most basal ones, and yet also the largest, showing how quickly birds filled the empty niches left behind by marine reptiles after their extinction. A Mesozoic fossil Lagerstätte from 250.8 million years ago shows a modern type marine ecosystem. The Permian-Triassic boundary is marked by the most severe mass extinction in the history of Earth. Over 90% of species died out, more than at the end of the Cretaceous. Paleontologists used to believe that the extinction was so devastating that it took many millions of years for marine ecosystems to recover step by step, with the early Triassic only providing for primary producers and primary consumers, with secondary consumers like crustaceans and ammonoids only appearing at the beginning of the Middle Triassic, and tertiary consumers like fish slightly later in the Middle Triassic. But now, Dai et al. Have described a fossil assemblage from the Dai Formation near Guiyang in South China. It is the oldest known Mesozoic Lagerstätte at 250.8 million years, just 1 million years after the Permian extinction event, and it already has a complex ecosystem with several different bony fish, for example coelacanthi forms. Maybe this assemblage represents a refuge where marine life was sheltered from the effects of the Permian extinction event, or maybe we underestimated how quickly life could recover from even the most devastating extinction event in the history of Earth, and that our sparse fossil record of the early Triassic is just a result of preservational bias. Triassic nursery? Evidence of gregarious behavior in juvenile pseudosuchian archosaurs as inferred by humoral histology of Aetosaurus ferratus, Norian, southern Germany. Aetosaurs were herbivorous Triassic crocodile relatives who basically were ankylosaurs before ankylosaurs were even a thing. The most famous member of the group is the large spiky Desmatosuchus from North America, but the name giver of the group, Aetosaurus, is a small featureless animal from Germany, only up to 1.5 meters long. The best Aetosaurus material is an accumulation of 24 individuals between 20 and 82 centimeters long from the lower Stubensandstein near Stuttgart. Teschner et al. Have sectioned two humeri from this assemblage, one of the smallest and one of the largest, to study their histology. Bone histology gives information about the growth of an animal and therefore its age, and these bones were highly vascularized and show no bone resorption or annual growth marks, indicating that these were juveniles that were not even 1 year old. With even the largest specimen being so young, it becomes more likely that the genus Aetosaurus is currently only represented by juveniles. There is a larger Aetosaur from the Stubensandstein, Paratypophorax, that may turn out to be the adult form of Aetosaurus. Another interesting fact about the assemblage is that it doesn't show any evidence of post-mortem transport, which means that all these juveniles lived and died together. Maybe they even originated from the same clutch. A giant phytosaur, Diapsida archosauria, from the Upper Triassic of India with new insights on phytosaur migration, endemism and extinction. Phytosaurs were carnivorous Triassic crocodile relatives who basically were crocodiles before crocodiles were even a thing. Hey, wait a second. Data and Ray describe a new Phytosaur species based on at least 21 specimens from a bone bed in the Upper Triassic Tiki Formation in India. The largest complete mandible is 1.1 meters long, with the entire animal estimated to be over 8 meters long, making it one of the largest known Phytosaurs. Hence its name, Colossosuchus techniensis. Phylogenetic analysis nests it within Mystriosuchinae, where it forms a clade with two other Indian Phytosaurs that have not been described yet. This is the earliest case of Phytosaurs endemic to Gondwana, despite the fact that Phytosaurs as a whole are distributed across the entire globe. Phytosaurs probably dispersed during the Carnian through inland waterways and along the Tethyan coast, with many taxa going extinct in the early Norian as the climate became drier. An ankylosaur larynx provides insights for bird-like vocalization in non-avian dinosaurs. Unlike humans and other mammals, reptiles have no vocal cords and can only produce sounds using their larynx made of cartilage, which is for example what crocodiles do. Modern birds have evolved a separate organ, the syrinx, to produce sound, and their larynx has become enlarged, ossified and kinetic, allowing them to modify the sounds produced by the syrinx. If you've ever wondered why so many paleontologists are ruining your childhood by saying that T-Rex would have been incapable of roaring, this is why. Non-avian dinosaurs do not have this specialized larynx and would thus have been incapable of producing complex vocal sounds. Or at least that's what we used to think until Yoshida et al. Described the larynx in a specimen of the Mongolian ankylosaur Pinacosaurus. It's the best preserved larynx in a non-avian dinosaur because it too is ossified. The larynx of Pinacosaurus is much more similar to modern birds than to other reptiles. The cricoid is large and wide, and the paired arytenoids are long and connected with a firm joint. These are the same adaptations that modern birds use to modify the sounds produced by the syrinx, which means that ankylosaurs might have also been capable of producing complex vocal sounds. It remains to be seen whether ankylosaurs evolved this bird-like voice box independently, or whether it was a far more widespread feature within non-avian dinosaurs that is simply usually not preserved or overlooked during preparation because of how delicate these tiny throat bones are. Modified skulls but conservative brains? The paleoneurology and endocranial anatomy of baryonychine dinosaurs Theropoda Spinosauridae. With their long, slender snouts and conical teeth, Spinosaurids clearly were to some degree specialized for catching aquatic prey and probably lived a semi-aquatic lifestyle. So you would expect their brains to also reflect adaptations for this lifestyle. That is what Barker et al. Set out to do by CT scanning the brain cases of two baryonychine Spinosaurids from early Cretaceous Britain, Baryonyx and Ceratopsuchops. And the special thing about these baryonychine's brains is how non-special they are. The team compared the brain cases to the endocasts of other, more typical theropods, and surprisingly found barely any differences. The inner ear is similar to abelisaurs and allosauroids, and would have allowed these theropods to hear low-pitch frequencies, and the olfaction is similar to ceratosaurs, allosauroids, and basal tyrannosauroids. A different study had previously looked at the brain case of spinosaurine spinosaurids like Irritator, and found them to have high-pitch hearing and reduced olfactory bulbs, which the authors had considered indicators for an aquatic lifestyle. Now, the baryonychine brain cases diminish the importance of these features. If the brain of a baryonyx is so similar to that of an allosaurus or ceratosaurus, it seems like any of these theropods had the theoretical pre-adaptations to evolve into a semi-aquatic niche, with the important factor not necessarily being to change the anatomy of the brain, but just to modify the snout and dentition. Giant Jurassic dragon lacewing larvae with lacustrine paleoecology represent the oldest fossil record of larval Neuropterans. Du et al. Describe a Neuropteran larva from the Daohugo beds, a Middle Jurassic Konservatlagerstätte of China. Paleoneurotus bayi is the earliest but also largest Neuropteran larva fossil known, with a length of 4.3 centimeters. Its elongated worm-like body, slender and elongated cervix, and straight jaws with curved tips most closely resemble available larvae of the modern neuropterans in the family Nephrotidae. These modern larvae are way smaller and live at the bottom of fast-flowing mountain streams, while Paleoneuratus was found in a shallow lake environment. It is possible that this spacious environment with more abundant food allowed this prehistoric neuropteran larva to grow so large. Like its modern relatives, its long cervix and long jaws allowed it to catch struggling prey without risking damage to its delicate abdomen. First Monot Dream from the late Cretaceous of South America. Modern and fossil Monot Dreams are only known from Australasia, with the exception of a single fossil from Paleocene South America named Monot Dream. Now Chimento et al. Described Patagorhynchus pasquale from the early Maastrichtian Carrillo Formation in southern Patagonia. While it is only a jaw fragment with a single molar, it definitely belongs to a Monot Dream, showing that Monot Dreams were already spread across Gondwana in the Cretaceous. So far, no Monot Dreams are known from northern Patagonia, but not just the mammals, but also dinosaurs differ in the north and south. Abelisaurids and Saltasaurines are found in northern and central Patagonia, while Megaraptorians and Colossosaurians are found in southern Patagonia. These different faunas probably reflect different environments, with a dry and warm climate in the north and a humid and cold climate in the south. In fact, other authors have even argued that some anatomical characteristics of Monot Dreams, like their low metabolism and electroreception, are results of evolving within a polar environment. A high-latitude Gondwanan species of the late Devonian Twistishopterid Haineria, Osteichthyes sarcopterygii. Twistishopteridae is a clade of Devonian sarcopterygians, which inhabited both the northern Old Red continent Euramerica and the huge southern continent Gondwana. Their most famous representative is the giant late Devonian Haineria, named after Haineer in Pennsylvania, which used to be the only place in the world it was known from. Now Guess and Ahlberg describe a new species based on skull bones from the Waterloo Farm Lagerstätte in South Africa. Haineria utlitzinie is the largest bony fish from the site, with the holotype estimated to be 1.8 meters long and one isolated bone belonging to an individual 2.7 meters long. Many Twistishopterids have been found in Australia, so the clade that Haineria belonged to was previously hypothesized to have originated in Australia and then migrated to Euramerica. Now it seems that this was just the result of collection bias, and Twistishopterids were so widely distributed throughout Gondwana that no precise locality can be pinned down as a point of origin. During the Devonian, this South African Lagerstätte was located near the poles, making Haineria utlitzinie the first known polar Twistishopterid.
But it's becoming increasingly obvious. I can deny it no longer. I am small.
A Devonian Fishtail. A new method of body length estimation suggests much smaller sizes for Dunkleosteus terrelli, Placodermi, Arthrodira. Ah yes, Dunkleosteus, the armored monster fish that famously outsized everything else in the Devonian. Or did it? You see, being an Arthrodire placoderm, Dunkleosteus had an ossified skull and thorax armor, but the rest of its skeleton was made from cartilage and thus never fossilized. All those spectacular claims of 8, 9 or even 10 meters in length never had any real basis. Sometimes smaller Arthrodire relatives known from complete fossils like Cocosteus are cited as the basis, but with their different proportions you would realistically get different size estimates for Dunkleosteus depending on which specific bone you use for reference. So, Russell Engelmann set out to find a proxy that would accurately estimate a fish's body size regardless of phylogeny, that would be consistent in extant fish whether shark or bony fish, and would also work for Arthrodires known from complete body fossils, and that would also be applicable to a fossil like Dunkleosteus that is only known from its head and thorax armor. The proxy he decided on was the length from the orbit to the opercula, as this is dictated by the fish's brain, orbit and gill chamber. These organs constrain body size because the gills cannot be too small to replenish the body with enough oxygen, but also not too large to require more energy than they would produce. Plus they have to be optimized for allowing the body to retain a hydrodynamic shape. Unless you are dealing with a fish that has a very extreme body shape, this proxy correlates pretty well. The simple rule is that a fish with a long shallow head will have a long shallow body, and a fish with a short deep head will have a short deep body. And Dunkleosteus has a deep head with deep armor. The most famous Dunkleosteus specimen, the skull and thorax armor at the Cleveland Museum of Natural History, measures 1.3 meters from the tip of the snout to the tip of the ventral shield and represents a typical adult-sized Dunkleosteus. And in Engelmann's analysis, its length is only 3.4 meters. But wait, you say, there are fragments of larger Dunkleosteus specimens, aren't there? Well, the largest known specimen is a lower jawbone 25% larger than the one of the Cleveland specimen, which would belong to a Dunkleosteus that was 4.1 meters long at best. It sounds shockingly short, but Engelmann also brings up another feature in Arthrodires, namely that the pelvic girdle is located just behind the end of the ventral armor. Like it or not, based on his calculations, a Dunkleosteus based on the fossils we have simply couldn't have been anywhere near as long as so many books and documentaries used to claim. But here's the thing all you salty Dunkleosteus fans don't understand. No matter how much Dunkleosteus is downsized, its skull stays the same. Engelmann even states directly in the paper, based on mouth size, a 3.5 meter Arthrodire can effectively fill the same ecological role as a 5.5 meter shark. Also, this shortened body shape just means that you should no longer see Dunkleosteus as an armored shark, but instead as an armored tuna. In other words, a cannonball with jaws. In other words, a freaking real-life bullet bill. This paper got such a huge reaction that Engelmann wrote a follow-up article in November to re-explain the science behind this, and his title was "What Shrunk the Dunk?", explaining the science behind a major update to the appearance of a prehistoric icon. Think about that. So many people were upset at Dunkleosteus getting downsized that the author had to make the scientific equivalent of a tweet-longer response and reassure people that his estimations are as reasonable as possible. If that doesn't make this paper the funniest thing to happen to paleontology in 2023, I don't know.
Hello, welcome to March 2023 of PaleoRewind. So, lips or no lips? That is the question that this paper tackles with Cullen and other authors. Theropod dinosaur, facial reconstruction, and the importance of soft tissues in paleobiology. Basically, the hypothesis that they are trying to tackle is beautifully illustrated in the first figure on this paper. That is, which is the most likely condition in the theropod dinosaurs we know and love? Well, it's either the unlipped or lipped condition. Again, figure 1, done by Mark P. Whitten, beautifully illustrates this. The unlipped condition is where we have the teeth splayed out, overriding the dentaries and profile view from the maxilla and the premax. Or do we have a condition where those teeth are covered nicely, sitting right next to the dentaries if you look straight at the head? And they couldn't really test this with birds, so they decided to go with Lepidosaurs, namely animals like Varanus, the monitor lizards, Ambularonychus, the Galapagos marine iguana. We also have like alligators, and they also even threw in an extinct early crocodilomorph, Hesperosaucus. And so they also did some histology on Daspletosaurus and the alligator. So they basically cut a alligator tooth and Daspletosaurus tooth, and they were basically looking at the structure. And so all this data kind of turned into a linear correlation graph where they found that the Tyrannosaurus and Gorgosaurus and Coelophysis, these theropods we all know, they correlate strongly with Varanus. And so what they concluded was the most likely condition is lips, and I'm sold on that. I've seen plenty of paleo art with lips, and I completely support that. However, I think that the sample size really needs to be expanded upon, especially with the histology, and I really just hope more studies will come out in the future. In other news, we have new fossils that push back the origins of ichthyosaurs. This is a publication done by Kier and other authors, where they uncovered a centra, which is like the circular base of a vertebra. And the centra is very big, it has a lot of spongy bone, and that's inside of it, and a lot of what they see is indicative of adult ichthyosaurian bone microstructure, and that's verbatim from the paper, which implies pelagic habitats, that is open ocean behavior, so more or less in that ecological area. On top of this, that also includes stuff like accelerated growth and elevated metabolism. Ichthyopterygians, that is ichthyosaurs and ancestors, emerging a lot earlier than expected with these traits that are key to them becoming very successful. The most interesting part about this find is hands down the age. It is less than 2.3 million years after the end Permian mass extinction. Speaking of early appearances of taxa, which are large-bodied, we have a new species of Whittia, that is a genus of coelacanth, described by Chase Brownstein of Yale University. And this novel species, known as Whittia giganteus, it comes from the late Triassic Dockham group of Texas. Two important implications I want to talk about here. Firstly, the size. Based on the holotype skull, which preserves the upper skull fairly well, despite being very eroded, more or less, along with the mandibles, it's clearly indicative of a large body size. And we don't typically see this early on in coelacanths, making Whittia giganteus the most massive member of its genus and one of the largest known Triassic actinistians, which that's the group which includes coelacanths and lobed-fin fish. And secondly, the phylogenetic analysis shows that Whittia giganteus plus the other species of Whittia, they share a node, that is, they share a split with the extant lineages of coelacanth and other lineages of extinct coelacanth, including things like the Mawsonid coelacanths, which Mawsonia is a part of, which this is an example of a coelacanth later on in the lineages which they achieve large body size. We're going to downsize a bit here, entering Veronov and colleagues' study here, Ontogeny and miniaturization of Alverasauridae. This is essentially a revision paper where they look at the known holotypes and specimens of the Alverasaurs. And this was a paper I unfortunately missed in my Alverasaurs Fuzzy Oddballs video, but to kind of summarize here, Alverasaurs, based on other studies, have been demonstrated to not really follow Cope's rule per se. Cope's rule is a biological idea where over time in a certain lineage, the more evolved they are, the more they progress, the larger they'll become as a lineage, that is, in body size. And Alverasaurs are an exception to this because they are miniaturized. However, this is all instantly skewed if you factor in ontogeny. Ontogeny is the study of the growth of organisms, and simply put, if your holotype is a juvenile, this creates problems with your diagnostics of a new taxon. If your holotype is a juvenile, how are you supposed to identify the adults? And so this is really what the paper goes into. Parvicursor, a genus of Alverasaur, was found to be a juvenile less than a year old based on histological approaches. Not only is Parvicursor recovered as a juvenile regarding the holotype, Achillosaurus, Aorun, Alverasaurus proper, these have juvenile holotypes. They'll turn problematic with time, of course, but other holotypes of certain taxa, based on fusions of certain forelimb elements, it demonstrates to paleontologists then that these are adult specimens, that these holotypes are good for defining certain individuals of certain genera. So overall, it's a very important paper to have come out, really trying to pin down the miniaturization of Alvarezsaurs throughout time. We generally have accepted that the center of mass of dinosaurs is more concentrated around the sacral girdle, that is, the hips. However, in birds, it's a lot more oriented towards the head, and the distribution is a lot more deep. This is something clearly revealed in this paper published in Nature Communications by Macaulay and colleagues. They basically use these new volumetric techniques to take a look at the evolution of the center of mass throughout time concerning dinosaurs and their ancestors. This not only applies to birds, but also the pseudoscians. That is, alligators, crocodiles, so on and so forth, and they even put in squamates into the analysis. They found that in the center of mass evolution in birdline dinosaurs, the second figure of the paper, that yes, the outgroup of all these reptiles are up top. However, as we go down, we see some overlap, namely in ornithomimosaurs, Megaraptor, and modern-day ostriches, or hummingbirds, dromaeosaurids, and tyrannosaurids, and kingfishers and pelicans occupying another morphospace. And it's very, very interesting. It's a very interesting paper, really trying to get at the origins of the modern-day Avalian bowel plan. They also found some very interesting data, such as Styracosaurus has one of the more caudal-based center of mass distributions, and so that's something hinting at the ancestral condition of, well, dinosaurs, non-avian dinosaurs. So, sauropods. They are the largest known terrestrial animals to date. Well, how did they get so big? Well, they had very light bones. They are pneumaticized. That's the word to describe them. They were hollowed out, and they took up a air sac system within life. And so, a lot of paleontologists have been thinking about where this invasive air sac system comes from. And that's what Orellano and colleagues sought out to do in this special issue article of the Anatomical Record titled "The Origin of an Invasive Air Sac System in Sauropodomorph Dinosaurs." A specimen of macrocolumn from the late Triassic of southern Brazil, and they analyzed it via microcomputed tomography. And they found that, well, it was pneumaticized. There were pneumatic fossa preserved. The air sac system was furthermore preserved. And this is actually incredibly significant, because this is at the moment, and I quote, the chronologically oldest and phylogenetically earliest unambiguous evidence of an invasive air sac system in a dinosaur, which is big news. Bureolestes, something that is more basal than macrocolumn, did not have this. They say that it's possible that this air sac system, this invasive air sac system, was not consistent in an evolutionary sense. However, over time, we do see throughout these forms, the sauropodomorphs, they do eventually normalize it into their anatomy. The study of trace fossils, that is, ichnofossils, is very important when you have a notable lack of vertebrate body fossils. And even if you have vertebrate body fossils, they cannot always be informative of certain lifestyles. And so this is especially pronounced in this paper titled "Unique Trackway on Permian Cruise Shoreline Provides Evidence of Temnospondyl Locomotory Behavior" by Groenewald and colleagues. This is a Permian age paleosurface site with the underlying formation being the Waterford Formation and the overlying formation being the Balfour Formation. And it's mainly indicative of a regressive deltaic environment. That is, it's a delta slowly becoming more influenced by loads of water. And at the site are trace fossils. They've been noted before in fieldwork efforts. However, the authors, they were very interested in what the trace fossils had to say. And they even found a large unidentified bone that compares favorably with the Dicynodont. But enough of that. What do the trace fossils have to say? Well, we have these circular round depressions with minimal ripple marks that dominate the site, which is indicative of, despite not being morphologically informative, indicative of a tetrapod track. This has mainly been attributed to Dicynodonts. However, they took a much more keen interest in these linear carved out incisions that they have interpreted to be resting positions of temnospondyls. They have also extrapolated from these trace marks that they swam with a sinuous kind of manner. So it's similar to sharks and how other fishes do it. It's a very interesting paper. I highly recommend you go read up on it. So before I go in depth on the final paper of PaleoRewind's March 2023 block, I have 5 papers I briefly want to give an honorable mention to. First, we have a new specimen of Sinosaurus triassicus from the early Jurassic of Lufeng, China by Zhang and colleagues. Sinosaurus is important as a taxon as it is a early large-bodied neotheropod, and like Dilophosaurus, Sinosaurus has this unique double-crested morphology. And this is why early on into its research, Sinosaurus was just diagnosed as an Asian species of Dilophosaurus. We know now this is not the case, and this was quickly pointed out. Sinosaurus, furthermore, doesn't really have a ton of remains associated with it, but this skull, it's beautiful. It is a beautifully complete skull that has also made the authors here proposed 3 new autapomorphies. We also have a new pterosaur paper, distinctive as darkoid pterosaur jaws from the mid-Cretaceous Cambridge greensand of eastern England and the Chem group of Morocco. This member of the late Cretaceous of England is Cenomanian in age, so the very first stage of the late Cretaceous is looked at here, and these specimens were originally identified as shark fin spines. However, the unique formina and morphology has led these researchers to reclassify these very fragmentary remains as edentulous jaws, which is indicative of an astarchoid pterosaur, as practically all taxa in Astarchoidea are edentulous. They don't have teeth. They also furthermore differ from the already named asdarchoid ornithostoma known from the Cambridge greensand. Based on the lateral surfaces, they're flat, which differs from the condition in ornithostoma, and they also have an acute dorsal ventral apex. That is the end of the jaw has a different morphology concerning the curvature. They are very similar to these other pterosaur jaws from the Chem of Morocco. This is especially notable as there's a lot of pterosaur diversity there. It's indicative of similarity in faunal assemblages, at least concerning the pterosaurs, between 2 distant locations, which is very, very interesting. And also we have here a new paleoanthropology paper, Knuckle Walking Sahelanthropus, Locomotory Inferences from the Ulnae of Fossil Hominids and Other Hominoids. This is a paper challenging the notion that the famous Tumai specimen, that is a skull uncovered from Chad, the country of Chad in Africa, it may not be upright. And this paper suggests that Sahelanthropus has a ancestral knuckle walking condition rather than the upright condition. So this challenges the notion of the course of evolution of us walking upright. So the final study I want to go over here is titled The Stability and Collapse of Marine Ecosystems During the Permian-Triassic Mass Extinction. This is a big paper. It could potentially change how we view the worst mass extinction to ever grace planet Earth, that being the Permian-Triassic mass extinction. And essentially what they revealed was, through quantitative approaches, that the ecosystem did not immediately just decline. Essentially what happened was there was a pre-extinction phase where we have a lot of diversity, but then that transitions to a big drop in biodiversity. However, the ecosystem was still relatively intact, and it wasn't until later, briefly later, we're talking about like a gap of 61,000 years, where afterwards we have a massive collapse in biodiversity. And this is something that can really change how we view this pivotal extinction event in Earth's history. It implies that a collapse in biodiversity predates more or less a ecosystem collapse, which is very, very interesting. And they do a lot of different analyses to demonstrate this.
First up, we have some newly identified species whose discoveries were first published back in April. The first being a species of bat that was discovered in the fossil lake deposits of the Green River Formation. Now, in general, bats coming out of this fossil location is actually nothing new. There have been several found here over the past 50 years, and this is actually the oldest known site where bats have come from, dating the only group of true flying mammals to the Eocene around 50 million years ago. But of all the dozens of specimens that have been unearthed from Green River over the decades, they have all been identified as one of two different species. That is, until the specimen was found this year, which not only was identified as a separate species, but was also the oldest of the three, pushing bat evolution back another 2 million years that we know of. Named Inoopteris gonelli, in addition to being the oldest known bat species, it's also the smallest of the known bats from this Eocene jungle. The Green River Formation is one of the most outstanding fossil sites for that time in the world, right up there with the Messel pits in Germany. It's constantly yielding amazing discoveries from the time when the world was recovering from the Cretaceous extinction and mammals were just starting to come into their own. But this next discovery is quite a bit older than Eocene bats, but it turns out to be another discovery to come out of Wyoming. This one, from the PaleoAnalysis Formation, dates all the way back 230 million years ago, during the late Triassic period. This was the time when the very first dinosaurs and pterosaurs were beginning to appear, and the world was finally recovering from the Permian mass extinction, which was the closest life ever came to being wiped out entirely. And as a result, there was a lot of vacant niches available in the Triassic. If you're a follower of my channel, I'm probably repeating myself quite a bit. We talked extensively about the Triassic over the years that I've been making content. And if you're a follower of mine, then you know that this time period has led to a lot of bizarre things in the fossil record that are entirely unlike anything alive today. But one of the most bizarre and arguably most successful during the later half of the Triassic is the Hyperodapodons. These little gremlin lizards kind of took over as the most common group of terrestrial animals after Lystrosaurus died out earlier in the Triassic. But I'll get more into that group as a whole in the next History of the Earth. But back in April, a new genus and species was identified with Bisiwocuus. Alright. This find was significant because although Hyperodapodons are pretty common in other areas around this time, they have been pretty much unheard of in the Paleoguy Formation, or just about anywhere in North America for that matter. Meaning, this discovery shows even more so that these Triassic oddballs had spread across the globe in the latter half of the Triassic. Next up, we get to talk about one of my all-time favorite groups of dinosaurs. The group that not only is considered the closest group to birds outside of the avialans, which are actually the birds, but have oftentimes been depicted as some of the most intelligent of the non-avian dinosaurs overall, the Troodontids. And this time, we found evidence that suggests not only some interesting anatomic findings, but also something that shows behavior. Now, pinpointing the similarities and differences between Troodontids and birds has been difficult, but a study done on several well-preserved Troodon eggshells have yielded some interesting results. Using a method known as dual-clumped isotope thermometry, they were able to determine the internal temperature that Troodon bodies maintained during gestation. They concluded that these Troodon eggs were produced between 30 and 42 degrees Celsius, or 86 to 108 degrees Fahrenheit. And by comparing the isotopic patterns found in these eggshells to what we see in the shells of both modern birds and the closest related reptiles to dinosaurs, we were able to settle a mystery. You see, unlike most other animals, female birds only have one ovary. Because of this, birds produce the shells of an egg much more rapidly than, say, reptiles do, since they can only do one at a time. This rapid creation of the eggshell leaves an isotopic pattern that can be detected, and this isotopic pattern was not present in troodontid eggshells in this study. This suggests that even in dinosaurs as closely related to birds as troodons, still maintained a reproductive system in females comprised of 2 ovaries rather than the one that we see in birds. And the scientists who made this discovery combined their research with the existing information concerning body and eggshell weight, and they concluded that female troodons could probably only carry around 4 to 6 eggs at a time. And this raised an entirely different mystery, because most of the nests that have been found of troodons were quite large, with up to 24 eggs. But it didn't seem that there was any possible way that a female troodon could carry 24 eggs at a time. The explanation for this is that possibly female troodons laid their eggs in communal nests. This would give them a better chance of survival in the late Cretaceous period, where there was an abundance of animals much larger than them that they would have had to defend their eggs from. This is a behavior that we see in several different species of bird today, one being ostriches, and even in the case of other birds that build in separate nests, they still tend to do so in the proximity of others doing the same thing. I still remember every spring when I would see mockingbirds all nesting in a single tree, and then they would mercilessly dive bomb any squirrel, cat, dog, human, or pickup truck that dared to get too close to the nesting tree. So it's a strategy that definitely works. So in conclusion, it seems that troodons still had a more reptile, or at least non-avian, reproductive system. But once they laid eggs, they adopted strategies that we would normally only really associate with birds.
Starting things off, on the 2nd of May, we had a very interesting paper that changed our understanding of the anatomy of Crassigyrinus, an early tetrapod. Crassigyrinus scoticus is known from fossils found in Scotland and Canada, dating to over 330 million years ago, and it was first described back in 1926. The new publication explained how previous reconstructions of this animal, which was a fairly large predator for its time, reaching up to 2 meters in length, had been based on specimens with incomplete and damaged skulls. This new research, though, used computed tomography methods to scan 4 different specimens and recreate the skull anatomy more accurately, finding that it actually had a much more flattened head than previous reconstructions. They also examined details of the jaw joints and the teeth, finding that Crassigyrinus was a very capable aquatic predator that was adapted for taking out large prey. So it was a very interesting revision of a unique early tetrapod, and it was also very nice to see Jenny Clack on the authorship, a legendary early tetrapod worker who sadly passed away in 2020. Next up, there was also a paper describing a new species of saber-toothed cat published in May. Amphimachairodus hejangensis was named based on a skull found in northern China that dates to between 9.8 to 8.7 million years ago. This is now the most basal or primitive species of the Amphimachairodus genus found so far, and interestingly it has quite sideways oriented orbits for the eyes, suggesting this cat was better at observing its surroundings rather than singling out specific prey, which the authors interpreted as being an adaptation to an open environment, or an indication of social behaviour. More evidence for social behaviour in these cats comes from the description of a forepaw, attributed to the Amphimachairodus genus, but not definitely to the same species, which shows a healed injury that would have badly impacted the individual's ability to hunt, and yet it obviously survived for a while after sustaining it, suggesting it may have been looked after by others. The study also analyses the rate of evolution of traits in these cats, finding that this new species represents an important transition that led to these animals adapting to open environments, and then eventually dispersing widely across the planet. It therefore seems as though the evolution of being suited to open environments and social behaviour occurred in this area near the Tibetan Plateau, as the region became more arid. A very significant paper there, with all sorts of implications for the evolution of this amazing group of animals. Also in May, we had a very intriguing new paper on the enigmatic Spinosaur Irritator challengeri, which made some pretty interesting discoveries about the feeding habits of this animal. The fossils known for Irritator actually represent the most complete skull of any Spinosaur found so far, and so using microcomputer tomography scan data of the skull, the authors refined our understanding of the cranial anatomy of this Spinosaur. Some of the main findings included the discovery that Irritator would probably position its snout at an incline of around 45 degrees when it had to look closely at the things around it, since this allowed the snout to stop blocking the view from the eyes, enabling for binocular vision, and therefore better depth perception. Another finding was that the jaws were suited to biting very rapidly, but relatively quite weakly, presumably an adaptation to catching fast-moving prey such as fish. But the most intriguing discovery, and something that's now inspired a great deal of paleo art, is that the lower jaw joints had a morphology that meant when the mouth was opened, the lower jaws would open out to the sides at the base, opening up the pharynx even wider. This sort of jaw function is also seen in modern pelicans, but through a different mechanism. So just to show that Spinosaurs can get even more bizarre, it turned out they had giant pelican jaws too. It should also be noted that the publication of this paper resulted in a lot of discussion about the return of the Irritator holotype back to Brazil, as it's currently housed in a museum in Germany. So another incredible development in the story of Spinosaur research. These dinosaurs really do never cease to amaze. Next up, we actually got a special report on the publication of some truly giant pliosaur vertebrae from the late Jurassic Kimmeridge Clay Formation of the UK, which also came out in May. We managed to get an interview with the lead author of this paper, Professor Dave Martill, who told us a bit about the background of this discovery and its significance to the ecology of late Jurassic oceans. You can see more of the interview in our 7 Days of Science episode on the discovery, but I thought it would be cool to include a little bit of it here too. Also, the interview was done while we were on a university field trip to Germany, so please excuse the slightly unusual setting. Anyway, here's me and the Boneheads crew with Professor Martill. So welcome everyone to this 7 Days of Science special interview with one of the authors of the new paper on this giant pliosaur, Dave Martill, and we're just here to ask you a few questions about this spectacular new find. So you're one of the advisors on Walking with Dinosaurs, famously creating the giant Pleurodon. So how did that come about?
Yeah, that's right. Well, thanks for inviting me along for a chat. That's good.
That's
good
all right.
to see you guys. When Tim Haynes was making the programme, he was sort of, if you like, running wild, trying to find what would be the best way to approach this, what would be the best animals to have, and where could we film it, and what sort of themes could we use. And he sent a researcher out to speak to all sorts of people and to discuss this. And I suggested that maybe they could use the Oxford Clay Sea as a theme. At first, they thought this was a bit strange because they were going to essentially do a programme containing lots of dinosaurs, of which very few are marine. And so he asked about what sort of star animals he could have in the programme, and I suggested that there was some pretty impressive marine reptiles, and when I told him about these animals he seemed pretty impressed, especially when I said that there were some giant pliosaurs and a giant fish called leadup. And I gave him lots and lots of star animals to choose from, but of course budgets were limited for making the pilot programme and a few things had to go, but a few things were essential. And I took Tim and the researcher to the Natural History Museum in London to show them some particularly large remains of pliosaurs that were very, very fragmentary. Pleurodon had been complete or near complete skeletons of Pleurodon had been found, and these animals are around about 6 meters long or something like that. But because there are these other fragments that indicate even larger animals, we had a go at trying to calculate the size of these animals with these fragments, and we weren't trying to be particularly accurate. There wasn't that much data around to be able to do proper scaling. And so we came up with a figure that quite a few people accepted as around about 18 to 20 metres as a large pliosaur. And not necessarily Liopleurodon, because we're using bits and pieces that could have belonged to other genera. And there was also material from the Kimmeridge clay formations, particularly a very, very large lower jaw in Oxford, which is getting on for sort of 3 metres long, huge thing. You drive a car into it. So what we did was we came up with this figure that I think it was about 18 metres or something like that, 20 metres. And then we realised that the data set was incredibly small. There really weren't that very many specimens of these animals known. And so we thought, well, you know, when you look at sauropods, from the very first discoveries of things like Cetiosaurus, which are fairly small ones, they've just progressively got bigger and bigger and bigger. More and more discoveries are made. Same is true of pterosaurs. And so we thought, well, maybe it's true of pliosaurs. So we added 5 metres. It's as simple as that. We just added 5 metres. And of course we got all sorts of criticism, but we never really got an opportunity to explain why we did that. We just thought we were preempting what might be discovered within the next 100 years. And it just sort of, it got put in there. Meg Jacobs, who's one of the authors on the paper, wanted to go to Abingdon to look at an ichthyosaur that they have, and so I took her up there, and while she was taking photographs of this ichthyosaur that's on display, I noticed that there were some drawers underneath it, and they were there essentially for children who were visiting the museum to pull open and see what's it, as though they're kind of going through the museum collection. And in one of the drawers I saw a huge vertebrae, and it was sort of this sort of diameter. But I know pliosaur vertebrae. I've collected enough, excavated enough pliosaurs to recognise one of their neck vertebrae when I see them. And I thought, that looks like a pliosaur vertebrae. So I asked if I could take it out of the drawer, and was given permission to do so. I photographed it, measured it and everything, and the curator said to me, he said, well, we've got 3 more of these. But they were in another location. So we went back and saw these other 3, and they have got all of the hallmarks of cervical vertebrae of a pliosaur, but they're actually from different positions in the neck. Now this gives us an opportunity to actually scale up. Now since the days of walking with dinosaurs, in those early days, many more pliosaurs have turned up, especially in South America, with complete cervical series, and that gave us an opportunity to scale up. But using some of these Cretaceous forms and late Jurassic forms, especially some stuff that's come from Mexico, places like that, we were able to develop a range of figures, if you like, of which the top is something like 14.2 metres. Which is an astonishingly large animal if you think about it, and it's way bigger than a killer whale, for example. So that's the story. We weren't excavating; we were pulling drawers open in a museum.
Thank you again to Dave for doing that interview with us, and what an incredible discovery. May also saw the publication of a very cool new paper describing a new species of large-bodied Gorgonopsian from South Africa. Gorgonopsians are the infamous top predators of the late Permian, a lineage of synapsids, related to our mammalian ancestors, that could grow to some pretty big sizes. The largest known Gorgonopsian is the 3.5 meter long Inostrancevia, represented by fossils found in Russia, and now also South Africa. 3 species of Inostrancevia were considered to be valid, all found in Russia, but this publication reported the first occurrence of the genus in South Africa, naming it as a new species, Inostrancevia africana. This was a very interesting discovery for several reasons, as before that paper, the largest South African Gorgonopsians had all belonged to a lineage known as the Rubigianae, which are only known from Africa and have notably broader snouts compared to Inostrancevia. But the presence of Inostrancevia here too suggests that a faunal turnover occurred among the top predators late in the Permian as the infamous Great Dying approached. The paper showed that the Rubigians appear to have been an early casualty of the disruption of terrestrial ecosystems just before the end Permian mass extinction event, and were actually replaced as top predators of the region by Inostrancevines migrating from elsewhere. But then the Inostransevines soon fell victim to the extinction too, with all Gorgonopsians disappearing by the end of the Permian, and then a different synapsid group, the Thericophalians, replacing them as top predators here, and then also going extinct in the Triassic. The paper explains how this relatively rapid replacement of different top predator groups illustrates the ecosystem instability around this time, with large terrestrial carnivores being some of the most susceptible groups to these dramatic changes. An absolutely incredible discovery which significantly expanded our understanding of Gorgonopsian evolution and distribution, and provided a fascinating insight into sequential extinctions of these large vertebrates. Now, I bet you thought there would only be one Spinosaur paper in May, but nope, another new Spinosaur paper was also published, this one naming a new genus and species from Spain. Named Protaphlitis cinctorensis, the genus name comes from the Greek for champion, and the material it's based on comprises a fragment of the right maxilla, an upper jawbone, and 5 tail vertebrae. Protaphlitis lived during the early Cretaceous, and it was classified as a basal member of the Baryonychine group of Spinosaurs, putting it as a close relative of Baryonyx, Ceratoseucops, and Suchomimus. The new species is from the same formation as Valibona venatrix, a Spinosaur named in 2019, suggesting that the Iberian Peninsula was inhabited by a diversity of Spinosaurids, including members of both Spinosaurine and Baryonychine subfamilies. Later on in the Cretaceous, they then migrated to both Africa and Asia, and it seems that in Europe the Baryonychines became dominant, while the Spinosaurines became more abundant in Africa. An interesting new addition to the known Spinosaur diversity then. Also that month, a new genus and species of Mosasaur was named. Called Stelladens mysteriosus, this animal is based on fossils found in the latest Cretaceous phosphate deposits of Morocco, and represented by a partial jaw along with 2 teeth. These teeth have a very unique shape though, being triangular and with a series of elaborate serrated ridges on the side of the tooth that would have faced the tongue. This unusual tooth morphology is what's given it the name, with Stelladens mysteriosus translating to star-tooth mystery. The function of these teeth in catching prey is not known, with the authors stating that it must have either had a highly specialized diet, a very specialized way of capturing prey, or a combination of both. The teeth don't seem to be particularly well adapted for catching fish or soft-bodied cephalopods, and they are also not that well suited to crushing down on hard-shelled prey. Hopefully more discoveries of this fascinating mosasaur can help to elucidate its diet. A new genus of Diprotodontid from Australia was named in May too. Diprotodontids were the biggest of the marsupials, including the well-known Diprotodon, which could reach the size of a rhino. This paper described some new material of a Diprotodontid called Zygomaturus kianii from South Australia, but found that this species is actually different enough from Zygomaturus trilobus, the type species of the genus, to be named as its own genus, and so it is now called Ambulator kianii. Looking at the characteristics of the limbs, the researchers found that Ambulator was graviportal, meaning it had adaptations for weight bearing, and found that it was better adapted to quadrupedal walking than earlier Diprotodontids were. This might be explained by the change in habitat that occurred as more open environments spread across Australia, meaning these animals had to walk further to find food. One of the most amazing things about this new paper though, is the fact that they also described soft tissue structures associated with the fossil, namely foot pads on the bottom of the left foot, showing how this animal supported itself on fleshy cushions. Sadly, the pads were actually prepped away from the fossil before they were recognised as soft tissue structures, and so they only exist in the CT scans of the fossil that were done before preparation. An absolutely amazing discovery of a new Diprotodontid then, adding to the known diversity of these wonderful marsupials. And finally, for the paleontological discoveries of May, we've got more fossils from Australia, as the oldest pterosaur remains in the country were also reported. Coming from the lower Cretaceous of Victoria, it's quite fragmentary but still clearly of pterosaurian origin. One of the fossils is a partial synsacrum, part of the hip, and the other is a left metacarpal fore, one of the bones of the wing. Characteristics of the bones mean that the synsacrum is from an indeterminate member of the Archaeopterodactyloids, or the Pteranodontians, whereas the metacarpal cannot be determined beyond being a pterosaur of some sort. However, the metacarpal is quite different from such bones reported from Australia before by being much smaller, and so the researchers suspect it is from a juvenile individual. Although they're very isolated bones, they do extend the known range of pterosaurs in Australia both in time and geographically, showing that these animals were able to inhabit high latitude regions and adding to the growing understanding of Australian pterosaurs. So then, May was an action-packed month for paleontology this year, as indeed most months were.
Hello once again, traveler, and welcome to the halfway point in PaleoRewind. Your journey has been exceptional so far, but you still have much more to go. I'm sorry, I'm just keeping up with the character every year at this point, I guess. Greetings, hello ladies and gentlemen, it is I, David, aka SpinoDude, back on PaleoRewind for 2023 to bring you the most exciting discoveries for June of this year. A big thank you to Edge for asking me to be part of this again, and let's not waste any time and dive into things. Introducing Inoopteris, a new ornithopod hailing from the Cedar Mountain Formation in North America. Known from a partial skeleton unearthed in 2014 and described as a new species just this year, Inoopteris was an early rhabdodontomorph, a lineage known almost exclusively from Europe. The name Ioni comes from the Roman god of transitions, Ionis, referencing that the animal came from a time of heavy environmental change. A very cool and important discovery for learning more about our beloved ornithopod origins. Another new dinosaur for ya, this time a Megaraptorion from China. Presenting Megaraptorion Claws. The theropod's placement within its clade is unclear, being known from rib fragments, a partial left arm, and a complete hand, but researchers have noted several similarities between Megaraptorion and the fellow Megaraptorion Fukivenator. This newly discovered small-bodied theropod roamed our planet during the early Cretaceous about 121 million years ago. In 2009, the holotype of a new species of extinct skink was unearthed in the Wellington Caves in New South Wales, Australia, dubbed Athesia frangens. Fast forward to 2013, a new species of blue-tongued skink was unearthed in the same location, named Tyrannosaurus laticephala. Fast forward again to 2023, and reevaluation of the available material by Kala Thorne and colleagues led to the renaming of Athesia frangens to Tyrannosaurus frangens, with phylogenetic analyses pointing towards a close relation being the modern shingleback. The same study also claims that T. laticephala could very well represent the same species as T. frangens with paramorphic traits present. These large armored skinks roamed New South Wales during the Pliocene and Pleistocene, and were probably adorable like modern-day skinks. I mean, look at this dude. New Ankylosaurian alert! Introducing Vectipelta barretti, or Isle of Wight's shield, hailing from early Cretaceous Wessex Formation. Vectipelta is the first ankylosaur described from the Isle of Wight in over 140 years, and may suggest that there are multiple taxa present among all the specimens previously assigned to Polacanthus and Hylaeosaurus from the same formation. The spearpoint ankylosaur, as it was nicknamed prior to its official description, is only distantly related to Polacanthus and Hylaeosaurus, however, being closer to the fossil superstar Borealipelta on the Ankylosauria tree. Vectipelta is known from a partial skeleton including several osteoderms. He was a bumpy boy. A new study of two separate Tanystropheus specimens show new evidence of a violent execution by Triassic hunters. These two specimens had very well preserved heads and necks that ended very abruptly, and in the new study, Dr. Steven Speakman and co-authors concluded that the necks had clearly been bitten off by larger predators. One giveaway was the fact that the head and neck of both specimens seemed incredibly undisturbed, suggesting that once separated from the body, they sank to the ocean floor and were buried. A really cool study on the predation tactics used on these long-necked Triassic reptiles. A new cetacean from the late Oligocene has been unearthed, and it had tusks? Well, kind of. Introducing Niohe matakoi, a tusk-toothed dolphin. The 25-million-year-old fossilized remains of this ancient whale were unearthed in New Zealand, and among the remains was a skull featuring conical tusk-like teeth. These long teeth had roots about twice the length of the crown and were likely fairly delicate in nature. The fossils of Niohe were unearthed in 1998, but were finally described just this year. Another year, another new mosasaur has been described, presenting Ceratosaurus dali, or the desert mirage lizard. This new plioplatic harpine was unearthed in Utah and is known from decent skull and axial postcranial remains. Ceratosaurus was fairly small, with estimations putting it just shy of 10 feet in length. The holotype discovered was a mature individual, being about 3 to 4 years old at the time of its demise. Another new whale? Yes, indeed. This time Olympocetus thalazodon, the second species from the genus Olympocetus. This cetacean from the Oligocene belonged to one of the earliest diverging groups of toothed whales known as Cimocetidae, a group known only from the North Pacific so far. The remains of O. thalazodon were recovered along the coast of the Olympic Peninsula in Washington State, USA, and feature strange heterodont teeth with differences along the tooth row, a look that contrasts the simpler, uniform teeth of modern Odontocetes. Quite a few new dinosaurs this month, this time Gongoken nanoi, the first hadrosauroid from Gondwana. Gongoken grew up to approximately 13 feet in length and represents the first non-hadrosaurid duck-billed dinosaur ever found in Gondwana. This fairly small hadrosauroid is known from quite a few disarticulated bones of multiple individuals, dating back to the late Cretaceous. What a cute little guy. And my final chosen entry for June of this year, this time some new research on the prehistoric superstar shark, Otodus megalodon. The study, led by Michael Griffiths and Martin Becker, used the fossilized teeth of megalodon to confirm that the giant shark's body temperature was actually much higher than we previously thought. Previous research has suggested that megalodon was very likely warm-blooded, just like some modern-day sharks, but this new study provides the first evidence of toasty bloodedness in the massive extinct celebrity shark, with the publication showing an average body temperature of about 27 degrees Celsius to be present. That is one big toasty boy.
Our first highlighted study is an analysis of molting in Megaraptorion dinosaurs, a clade that includes the lovely chicken parrots, dromaeosaurids, and modern birds. Molting is the process by which feathered animals shed old feathers to make way for new ones, since feathers don't repair themselves and need to be completely replaced when damaged or worn. Complete molting in modern birds is normally on an annual cycle, but it's very difficult to determine in fossil animals. The only confirmed molting dinosaur fossil we have is a single specimen of Microraptor, which was replacing some primary feathers in its right wing when it died. The study's authors, Joseph Kiat and Jingmai Kathleen O'Connor, performed a survey of 92 other fossils of non-avian and avian dinosaurs, searching for indications of molting, and they found none. Interestingly, the statistical distribution of preserved molt traces mirrors the proportions of modern bird collections that engage in rapid simultaneous molting, which is a much faster process and is less likely to be preserved. This indicates that early Megaraptorion dinosaurs may have engaged in very short, quick molting periods, with the longer-lasting sequential molting evolving in more derived birds later on. Now we go back in time even further to the Cambrian, the period when the brainchildren of George Lucas ruled the oceans. You can't look at Opabinia and tell me that it doesn't belong in Mos Eisley Cantina using its face as a space saxophone. I mean, come on. Anyway, a paper led by Russell D.C. Bicknell took a look at the world's first apex predator, Anomalocaris, the abnormal shrimp. While not a shrimp, this spike-tentacled-faced beastie was certainly abnormal. In a world filled with small, crawling critters, it was a 3-foot-long carnivorous swimmer. And despite its recent portrayal as a trilobite cruncher in the Netflix series Life on Our Planet, this study indicates that its raptorial appendages weren't designed for piercing armor. They actually would have been damaged if they'd tried. Instead, biomechanical modeling based on giant vinegaroons and tailless whip scorpions shows that they were better adapted for rapid capture of soft-bodied prey. Ecologically, it seems most likely that Anomalocaris hunted soft animals that swam in the water column, although other related radiodonts may have been better adapted for durophagy. The Permian, in my opinion, is the most underrated prehistoric time period, mainly because it produced the Gorgonopsids, one of the coolest animal groups ever. They were carnivorous therapsids ranging from small dog to bear size, and are famous for their iconic saber teeth. They may have even had parietal eyes, light-sensitive patches on the tops of their skulls seen in some modern reptiles like Tuataras. And while this description isn't reflective of their actual taxonomic status, I like to think of Gorgonopsids as reptilian saber wolves. A study published on July 7th described a Gorgonops skeleton with relatively complete postcranial material, allowing for study of its morphology and inference of its ecology. This individual would have weighed about 98 kilograms, and its well-preserved forelimbs are proportionally similar to those of the cat-like ambush predator Thylacus smilus. Vendel and her team speculate that the overall build of the animal indicates that Gorgonopsids were ambush predators that used their powerful hind limbs to pin down their prey before finishing them off with their saber teeth. Quite the evocative image. Another July highlight examines how archosaur nesting strategies gradually changed from crocodile-like to bird-like. Hogan and Varicchio's analysis points out that crocodilians are ectotherms that bury their eggs in vegetation, which rots and outputs enough heat to successfully incubate the eggs. Birds, on the other hand, are endotherms that use contact incubation to regulate egg temperature. So how did archosaurs evolve from one behavioral extreme to the other? As it turns out, the fossil record of Megaraptorion dinosaur eggs shows partially buried eggs, exactly what you'd predict to find as a transitional behavior between crocodile-like and bird-like nesting. Partial burial confers advantages like temperature regulation, camouflage, and the ability of the parent to check on the eggs without needing to dig them out of the ground. Some shorebirds still do that today. Speaking of crocodile-like, a new species of alligator was described from the Quaternary of Thailand. Gustavo Darlem and his team examined an extraordinarily robust Chinese alligator skull and determined via CT scanning that it was likely its own species, which they named Alligator munensis. It was discovered in the same layer as the remains of a water buffalo and sambar deer, giving us an idea of what it would have fed on in life. The new species has a shorter, thicker skull and fewer teeth than the Chinese alligator, and morphological analysis implies that it had a crushing bite adapted for hard-shelled prey items. It's adorable, but it would also be happy to rip your head off. Crocodilians really are the best of both worlds. While you may have seen my analysis on how Cenozoic megafauna would fare in the Triassic period, I'm happy to report that we don't need to rely on speculative ecology for our childish fantasies of dinosaurs fighting mammals. Han et al. Describe an incredible find. A Rapenomammus, a badger-sized gobiconodontid, locked in a death match with the early ceratopsian Psittacosaurus. We'd found remnants of hatchling Psittacosaurus inside Rapenomammus stomachs before, but this is the first time that two adults had been discovered in combat. The amazing fossil was from the Yizhan Formation in China, one already well known for its extraordinarily dense Psittacosaurus population. I don't blame the Rapenomammus at all. If there was such an abundant food source, why not go for it? The preservation shows that the mammal was gripping the much larger animal's jaw and biting its ribs when all of a sudden a fast-moving lava flow buried them both. While the authors say that scavenging was a possibility, they also mention it was very unlikely given the position of the animals and the lack of scavenging marks on the Psittacosaurus itself. I've got to admit, it's difficult to get more awesome than a dino versus mammal showdown in a chaotic volcanic landscape. Our final mention is short and sweet. I know how excited you are to get to August. Zhang Zhuo et al. Described two new saber-toothed cat species from Pliocene Africa, Locotunjailurus chinsmaye and Dinofelis wardellini. They were described from the Langebanweg quarry in South Africa and are part of a half-dozen saber-toothed cat species in the area, confirming the study's claim that it really was an evolutionary hotspot for saber-tooths.
Welcome to the August segment of this year's PaleoRewind, organised by the YouTuber Edge Science. I'm George the Dinosaur Guy, and I was invited to narrate this video on behalf of Nature's Compendium. In this video, we will focus on 3 interesting and rather significant extinct ocean animal discoveries published during August 2023. Diving right in, we have one of the most incredible discoveries of the year, an animal that may be the largest fossil vertebrate ever discovered, Paracetus. Paracetus colossus was a massive prehistoric whale uncovered from the Paracas Formation in Peru. It is the largest basilosaurid known to date and was described and published on August 2nd, 2023. the animal lived around 39.8 to 37.8 million years ago, during the Middle Eocene. The holotype specimen included 13 vertebrae, 4 ribs, and some parts of the pelvic region. The animal is believed to have measured up to 18.3 meters long. However, there is still some contention on how much it weighed. Due to the density and robustness of its bones, weight estimates have varied from anywhere between 85 and 310 tons in its description paper. However, more conservative estimates place the animal's weight at anywhere from 60 to 75 tons. To find out more about this colossal cetacean, be sure to watch Nature's Compendium's full video on Parasitus. Interestingly enough, the next animal we have is one of the smallest basilosaurids known, Tutsitus. Tutsitus was published shortly after Parasitus on August 10th, 2023. The Tutsitus specimen published is considered close to maturity, and it only measured 2.5 meters, or about 8 feet. It also only weighed around 180 to 187 kilograms, or 398 to 412 pounds. And finally, we'll travel all the way back to the early Triassic to meet a basal ichthyosauromorph named Hooposuchus. Now, Hooposuchus was originally found in China and described and published back in 1972. However, 2 new specimens have revealed some exciting insights into these animals. The 2 specimens gave paleontologists a better look into the animal's skull anatomy, and these findings were published on August 8th, 2023. They discovered that these animals' skulls were highly similar to modern baleen whales. The similarities include an unfused upper jaw, specialized intermediate space in the divided premaxillae, and grooves around the outer edge. The space in unfused bones would have let Hooposuchus expand its mouth to gulp in a lot of water. Furthermore, the grooves indicate that baleen-like soft tissue would have been present for filter feeding. Hooposuchus was a rather robust and rigid-bodied animal, and likely did continuous ram filter feeding like modern bowhead whales. The early Triassic paleo environment of a restrictive lagoon with low productivity drove Hooposuchus to feed on zooplankton. It's amazing how marine reptiles recovered and adapted to all kinds of niches after the Great Dying at the end of the Permian.
Discovered from Lower Cretaceous rocks in Spain, a new titanosaur named Garumpa was described from remains located in Morella, which were found to clade within the Symphospondylans, a group which includes titanosaurs, among the largest known sauropods, as well as their close relatives, excluding the brachiosaurids like Brachiosaurus and Giraffatitan. One of the more basal members of the group, this new genus is known from good remains, with 3 individuals being known of, with 2 complete and articulated feet being found, which is very rare in the geologic record. The sauropod fauna of the region during the time they lived, which includes both northern Laurasian type animals as well as southern Gondwanan forms, shows that an interchange of animals from these 2 regions was indeed possible and happening, which is quite a bit more impressive considering the Iberian Peninsula and much of Europe during the time was a series of islands. So, with the addition of Garumpa, this allows for much more important information to be gleaned to better understand the initial evolution of a group of sauropods that would go on to be among the most dominant in the latter part of the late Cretaceous. Moving on from among the heaviest of large animals to some of the lightest, an incomplete yet still decently sized rostrum and vertebrae of a pterosaur from the late Jurassic rocks off the Lourinhã Formation in Portugal was described, the first to be named from the region. The specimen exhibited some peculiar features such as a spatula-shaped rostrum as well as comb-like dentition, which suggested their affinity for being a Gnathosaurin pterosaur, a group related to unusual members of the wider family Ctenochasmatidae, like the filter-feeding Pterodastro. Named as Lucignathus, pterosaur material from the region was very scarce before their description, with the remains that were known of before often being fragmentary isolated bones and teeth, a testament to the fragility of pterosaur skeletons, which were heavily pneumaticized and filled with air. Lucignathus, based on the size of their rostrum, would have been among the largest pterosaurs of the time, with the known preserved rostrum being about 20 centimeters long, though could well have been larger. Through scaling the specimen of Lucignathus to a related Gnathosaurus, the total length of Lucignathus' skull would be a good 60 centimeters long, with them then having an extrapolated wingspan of about 3.6 meters at a minimum. This is all the more impressive when pterosaurs of the Triassic and Jurassic have been traditionally thought of as quite small animals, very rarely having wingspans of 1.8 meters or more, so the description of Lucignathus goes a good way in terms of our further understanding of pterosaur diversity and how they reach large sizes quite early on. Pamphonius bicae are large dinocephalian therapsids that lived in what is now Brazil during the Permian periods around 250 million years ago, were a group of animals with both carnivorous and herbivorous representatives, which were among the most diverse of large terrestrial animals when they were alive. At estimated sizes of about 3 meters and weights of about 400 kilograms, Pamphonius were among the largest of these animals. Known well for their solid set skulls, Pamphonius was among this group in being a no small member, though until recently was only known from its holotype, meaning not too much was known on them. This was until September of this year, when new fossil material from them was described, with a complete skull and some additional bones like ribs and arms being found in the rural area of São Gabriel in southern Brazil. This find is very important, as this skull is the second ever to be discovered from the genus, with it also being larger than the holotype, now thought to be a subadult animal, revealing unique information on their growth and morphology due to the great preservation. It was previously hard to differentiate them from their European relatives, so the more that's known from them allows for more about their proportions and overall evolutionary relationships with other dinocephalians to be understood. The early phases of birds transitioning from non-avian theropod dinosaurs is quite unclear, owing to the very sparse fossil record of the time periods when this was all occurring, namely the late Jurassic. Thankfully, one new find represents one of the youngest and also among the most southernmost Jurassic avians. Named as Fujianveneta from the Tithonian age of China, this specimen exhibits a range of unusual features that are shared with other stem avians, troodontid and dromaeosaurs, showing a good degree of overlap. Fujianveneta is distinct from all other Mesozoic avian and non-avian theropods in having a particularly elongated hind limb, suggestive of a terrestrial or wading lifestyle, which is in contrast with other early avians, which exhibit more clear adaptations to arboreal or aerial environments. This is down to their lower hind limb, their tibia, being twice as long as their femur, which is a previously unknown arrangement seen in these types of animals. To conclude this video, I'll be leaving off on a recent paper which talks about Trilobites, a very well known group which is known for more than 20,000 species, with them filling an exceptional array of lifestyles, from burrowers to a planktonic life in the water column. Their inferred niches range from being detritivores to active predators, though this has all been based on indirect evidence such as body and gut morphology, as well as attributed feeding traces. No trilobite specimen has ever been found with direct internal contents before, that is at least, until now. This right here is Behemolycus incola, a rather neat trilobite that lived during the Ordovician period, and preserved a three-dimensionally intact digestive system and complete with food too. This specimen provides by far the most detailed source of information to date concerning the diets and feeding mode of their group, with their last meal being identified and the researchers who described them remarking that they were absolutely stuffed. Their gut comprises mostly of fragmented calcareous shells, which along with their lack of dissolution indicates that a neutral or alkaline environment was present along the length of their intestine, which shows that their digestive enzymes were very comparable to living crustaceans and chelicerates. This digestive physiology therefore seems primitive to arthropods as a whole, with Behemolycus seeming more like a scavenger than an active hunter based on what's been found in their fossilised digestive system. Something that was noted was that the carapace of the trilobites was slightly disturbed in how it was organised, which suggested that the trilobite was in the process of molting before it ended up being buried and fossilised, with living arthropods sometimes using the technique of puffing themselves up to better crack their old exoskeleton so that they can better grow out of it. Another interesting observation that was noted was that the fossil trilobites also showed evidence of burrowing by other scavenging invertebrates, with them trying to get at the trilobite soft tissue before they were buried, seemingly stopping short when getting to their guts. This might be down to the trilobite's digestive tract having some sort of noxious condition within it that made it not very appealing even for scavenging animals. All in all, this fossil is an incredible first window into life as a trilobite, and another example of how rarely preserved intact remains can reveal so much about not just a long extinct animal, but also their environment in the process.
Dawn of the magical Leopleurodons. Pliosaurs were without a doubt some of the most ferocious ocean predators ever to scour Earth's waters. With these short-necked, giant-jawed plesiosaurs getting an almost explosive start during the Jurassic. And in 2023, the Jurassic origins became even clearer with the description of Lorrainosaurus killeni. Formerly a species of Semolestes, Lorrainosaurus not only marks a new genus of pliosaur, but also marks a new time these giants came to be, having been uncovered from a time very early in this lineage's evolution, around 170 million years ago. This not only showcases how early pliosaurs evolved into macropredators, but speaks to the wider ecology of the early to middle Jurassic transition, with the study in question describing that Lorrainosaurus came from a time that was in the midst of a faunal turnover, or a phenomenon in nature characterized by the synchronized disappearance of organisms and the appearance of new ones to take their place. And it seems that this turnover may have played a role in allowing Lorrainosaurus and other giant pliosaurs to grow and evolve into apex predators into the late Jurassic and early Cretaceous. Talk about taking a bite out of history. Ankylosaur edibles. Ankylosaurs are known for many things: their armor, their club tails, and sometimes even their colors. But there's more to these animals than meets their armored eyes. 2023 not only marked the 100th year birthday of the group Ankylosauria's classification, but a wealth of studies and discoveries diving deep into the other side of these mysterious animals. One of these studies, published in October 2023, examined the different feeding strategies of ankylosaurids and nodosaurids, utilizing the skulls of two of the most important well-studied genera of each group, Euplocephalus and Panoplosaurus. The study revealed that between these two skulls, Panoplosaurus had a more efficient jaw structure than Euplocephalus, and by extension, similar-jawed nodosaurs also shared this efficiency, which may have been a key adaptation to this group's success as they spread worldwide. By contrast, while Euplocephalus had a less efficient bite mechanically, its larger size and boxier muzzle meant it was able to bite harder and chew through tougher plant material. This speaks volumes to how these animals not only had different diets, but were able to coexist as two groups of armored dinosaurs living at the same time in the same place. Rise of the Dark Knights. As creatures of the night, bats have had millions of years to hone some of their most specialized adaptations. Adaptations that have allowed them to become one of the most numerous species of mammals to ever scour the skies, with the wings of over 1,400 species flying around today. One of the many traits that have made bats so successful is the evolution of echolocation, and a study published in 2023 showcases how far back this astounding adaptation goes. A new genus of bat was described, called Valesia, which was discovered from a cave deposit of the early Eocene, having been deposited 50 million years ago. Its well-preserved skull showcases signs that it was already on the fast track towards echolocation extremely early in the evolution of modern mammals. To put things into perspective, bats were not only living in caves only 4 million years after the extinction of the dinosaurs, but had already begun to evolve adaptations for echolocation this early. Now who's to say bats can't have superpowers? Yellowstone's first dinosaur. Dinosaurs are extremely well known from the American West, and many were at their most numerous throughout the region during the Mesozoic. And while they may not roam the earth in the same way they did millions of years ago, many new giants have risen to take their place in the prairies, forests, and mountains that have made places like Yellowstone so iconic, while modern dinosaurs continue to soar above the skies and forage along the rivers of this natural wonderland. But beneath the wings of eagles and the trampling feet of buffalo, the fossils of long-lost giants remain. In October 2023, the first ever Yellowstone dinosaur fossil was finally described: the isolated tooth of a young Tyrannosaurus rex. A study of the isolated tooth that was found in the 20th century, this young T-Rex tooth is the first of any dinosaur fossil to be found in Yellowstone, and it really begs the question, what other slumbering giants lay beneath the rich soil of Yellowstone? The world serpent. The last and biggest discovery on our list comes from an ancient serpent, one that roamed the ancient seaways of Cretaceous past. A brand new genus of mosasaur called Jormungandr, named after the giant serpent of Norse mythology, destined to bring about Ragnarok and battle Thor at the end of time. While this genus wasn't swallowing the earth at its modest size, our new mosasaur is upending what we thought we knew about mosasaur evolution. Recovered from a nearly complete skull, Jormungandr is especially notable for possessing traits of both primitive and derived mosasaurs, and may potentially represent an intermediate stage between its close cousin Clydastes and the later gigantic Mosasaurus. What's even more remarkable is that the specimen on hand isn't just a treasure for its traits, but the wounds its bones preserved, showcasing several bite marks made by other mosasaurs, and may have even been killed due to these bite marks. They may not have been the world serpent, but this mosasaur certainly earned its way to Valhalla. A Psittacos century. Saving the best for last, October 2023 marked the 100-year birthday of the dinosaur that keeps on giving, Psittacosaurus. Described and named in 1923, this dinosaur has become one of the most well-known, well-sampled, well-studied dinosaurs in the fossil record, not only giving us rich samples of fossil bones, but providing a wealth of information that has shaped paleontology for over 100 years. Here's to you, Taco!
Alrighty, so you're done watching Omega Studios' segment for October. Now I have your attention for November of 2023. This month didn't see a huge number of headline-breaking discoveries, but it did see a bunch of rather interesting discoveries in ichnology, dinosaur behavior, and the evolution of modern animal lineages. I threw a story about a new dinosaur in there too, for all the dinosaur nerds out there. So without further ado, November 2023. Did birds originate in Triassic South Africa? For the longest time, the earliest form of bird-like animal was Archaeopteryx from Jurassic-aged German rocks. In the last almost 30 years, a handful of other proto-birds have been recovered from similarly aged rocks across China. However, all of these animals are advanced enough to carry a pair of asymmetrically feathered wings adapted for flight, even if that flight may not have been as good as birds today. These theropod dinosaurs and the morphological changes in anatomy from other theropod dinosaurs and into the more advanced true birds shows that the origin of birds is deeply nested within the Megaraptorion group, the huge group containing the Alvarezsauroids, Therizinosaurids, Oviraptorosaurians, Dromaeosaurids, Troodontids, and birds, plus all of their weird intermediate cousins. This means their true origin has to stretch back before the late Jurassic, with some molecular studies suggesting an early Jurassic origin. Some experts think they may have even originated during the Triassic. However, there is yet no skeletal evidence of bird-like animals from the Triassic. There is one single purported bird specimen called Protoavis, but this thing has so many problems with it that I don't even want to get into it here. Suffice it to say, the thing is incredibly dubious, and the majority of scientists agree it does not represent what its descriptors say it represents. Okay, so no body fossils. Does that infer something else exists? Well, maybe sort of. Fossil footprints help to broaden the worlds of the past in a way body fossils could never. They help to capture far more animal diversity in a given time and place than bones can. Theropod dinosaur trackways have been known to science for pretty much as long as their bones have, with a good case for their existence being known to human cultures for hundreds to thousands of years. Due to birds being theropod dinosaurs and retaining a similar general foot structure, their footprints look pretty much the same. Fossil footprint experts can usually tell the difference between avian and non-avian dinosaur footprints due to birds having weird arrangements of toes that many non-avian dinosaurs didn't have. But ambiguity can still sneak its ugly face on in there. To that end, there have been bird-like fossil tracks described in the scientific literature for over half a century that have given researchers headaches. Do they represent the true first birds, or are they just non-avian theropods with unique feet? These tracks are called Trisauropodiscus and are known from several sites of late Triassic to early Jurassic age in South Africa. November of 2023 saw the publication of a paper by Mienga Abrams and Emis Bordi in PLOS ONE that takes another look at the previously described Trisauropodiscus footprints to determine whether they should remain as a valid ichnotaxon or be subsumed by the ichnogenus Onomapus, as has been the case for many decades. They found that there were two distinct types of Trisauropodiscus footprints that could represent two different types of animals. Both types come from the Lower Elliott Formation, with one type of footprint being more avian. This they labeled Morphotype 2. Morphotype 2 is said to be very bird-like, but that they don't contain quite enough of the little anatomical markers that confirm a true avian identity. So the researchers hypothesize that these footprints belong to a very bird-like archosaur, meaning that the avian foot morphology originates around 210 million years ago. Birds simply convergently evolved the same foot type. First modern hippos did as the Romans did. The fauna of many parts of Africa today, in some ways, reflect the general faunal diversity that once covered much of the world. Elephants, hippos, rhinos, lions, leopards, giraffes, camels, crocs, pythons, baboons, monkeys, and so many other animals that many of us Westerners identify with Africa were prevalent throughout Africa, Europe, and Asia for millions of years, with many of these groups making it into North America, where they thrived for quite some time. Getting the gist of how these animals evolved into the various forms that are found in the fossil records of these variously happening places can help to better understand the connection between animals and climate. One such example is the presence of hippos throughout Europe for hundreds of thousands of years prior to the last glacial maximum. Their presence indicates the presence of large bodies of water and warmer temperatures, since their skeletal remains don't deviate from the general hippo body plan seen in today's hippos. They've been water horses for a majority of their evolutionary history. One interesting hippo skull from Rome proves that the animals had been thriving in the region for a lot longer than previously thought. A huge team of Italian and German scientists published their work on this skull in a November 2023 PLOS ONE paper. A hippo skull was found in the Tor de Quinto area of Rome during the early 20th century, finally getting a description in the 50s. However, the skull was completely removed from its context. So how old it is had to be estimated based on what was already known of hippo evolution, the region's paleontologic history, and local stratigraphy. Most of these Roman vertebrate fossils come from the mid-Pleistocene or Chibanian-aged Valle Giulia Formation, 560 to 460,000 years ago. So that was the general estimate. However, the skull was usually kept out of most discussions on hippo evolution in Europe because of the gray area of its provenance. The new research team took another look at the skull. They found sediment still lodged in some cavities of the noggin, which was the perfect piece of evidence they needed to figure out exactly how old it was and where it had come from. After doing some petrographic and sedimentological analyses on the sediment, they were able to confirm the skull had come from the Montanari quarry, making it Middle Pleistocene in age. The team also did some morphological analyses on the bones themselves and found that the skull belongs to the still-living hippopotamus amphibious species, making it the oldest known specimen of the modern species. Ice Age Australia gets new raptors. Australia has a pretty alright fossil bird record. There's a bunch of flightless birds because, Australia. However, the Australian fossil record for birds from the Pleistocene that aren't flightless birds is kinda lame. There are pretty much only 3 unique extinct species of raptors from the Ice Age: Necrastur alasur, Cryptogyps lacertosus, and Dinotoatus gaffae, all of which belong to the Accipitridae family of eagles, hawks, and vultures. Some of this lack of diversity in Australian Ice Age raptors could be due to the wonky climate changes in Australia. It got super dry there during the Ice Age, and it hasn't gotten much wetter since. Other groups of raptors are present today in islands near Australia because they have better climates for them. A paper was published in November of 2023 in Alcaringa, an Australian journal of paleontology, that describes 2 new specimens of raptors from the Ice Age, one of which turns out to be a new species, increasing the Australian Ice Age raptor diversity. The author team reevaluates all of the known Ice Age raptor fossils and fossil sites and describes some new ones. They described some material from the small vulture Cryptogyps lacertosus from Site 7 of the Green Waterhole or Fossil Cave of Tantanoola District, South Australia, plus some more remains from Liana's Breath Cave, Wellington Caves, and the Walleye Caves. They also describe new remains of the Australian wedge-tailed eagle, Aquila audax, from the main fossil chamber of the Victoria Fossil Cave in Naracoorte, South Australia, dating to the early to middle Pleistocene, about 300,000 to 150,000 years ago. Their huge report also includes indeterminate remains of accipitrids from the Wellington Caves of New South Wales and Liana's Breath Cave of Western Australia. And lastly, they have some remains of what they justify as a new species, Dinotoatus pachyosteus, a large eagle that come from the same main fossil chamber of the Victoria Fossil Cave as the wedge-tailed eagle. So, now the Ice Age of Australia has one new bird of prey. Just chicken scratch? Moa is the common name of a group of giant flightless, armless birds related to the still-living tinamous that were the main terrestrial animal in New Zealand until their complete and utter eradication by humans in a span of around a century, about 600 years ago. Somehow. There were 9 species, with the largest standing around 12 feet, 3.6 meters tall, and weighing 510 pounds, 230 kilograms, and the smallest being a bit taller than a large turkey. Their fossil remains are numerous, but their footprints are not so common. Over a handful of fossil moa trackways have been discovered in New Zealand's North Island, but only 2 have so far been found and documented in the South Island. One set of footprints found in Kyburn, Otago in 2019, and a second set of a few footprints alongside the foot bones that made them in 2022 in Pairoa, south of Timaru, South Canterbury. The second set have not yet been described, but a description of the first set was published in November of 2023 by a team of researchers from Dunedin and Wellington, New Zealand, and Sydney, Australia, in the Journal of the Royal Society of New Zealand. The Kyburn tracks consist of 6 footprints that were on average 4.6 centimeters, 1.8 inches deep, 27.2 to 30 centimeters, 10 to 11.8 inches wide, and 26 to 29.4 centimeters, 10.2 to 11.57 inches long. The team collected all 6 footprints by cutting them out of the rock they were lodged in, since cutting out the entire trackway in one piece would have likely been very difficult. In order to even get to these prints, they had to redirect the river that ran over them. After the team collected the prints and did some 3D photogrammetry of the original site, they found that there was a 7th print from a different moa that was bigger, 44.8 centimeters, 17.6 inches wide, and 28.5 centimeters, 11.2 inches long. Because there were no bones nearby, the author team can only speculate as to which moa species left the tracks based on size and what species were alive when they were made, which they found to be around 3.57 to 2.9 million years ago, the late Pliocene to early Pleistocene. The identity that could best fit is supposedly any species from the Emiidae family. The authors hypothesize the genus Pachyornis is the most likely. The authors think the single larger print may have been made by a species from the Dinornithidae family, such as a species from the genus Dinornis. Albatross around the neck of albatross evolution? The vast majority of albatrosses alive today soar on hot air throughout the southern hemisphere, with few making a go at the North Pacific Ocean. Despite this modern range, the crappy fossil record of the albatrosses is at its best in the northern hemisphere. This contradiction tells you that they were once pretty much worldwide. Daniel Kasepka, Alan Tennyson, Marcus Richards, and Robert Ewen Fordyce published a paper on a new specimen of prehistoric albatross in November of 2023 in the Journal of the Royal Society of New Zealand. One of the best-known southern hemisphere genera of fossil albatrosses is Platornis, and it has a long and obnoxious taxonomic history I don't think I want to delve into here. The specimen they described in this paper, chunks of the skull, some vertebrae, some limb bones, and some leg bones, was discovered on a field trip all the way back in 2010 during the excavation of a whale skeleton in the same quarry. After collecting and cleaning the specimens, the researchers found that it had enough unique traits to separate it from all known species of the Platornis genus, so they named it Platornis archaeonautis. This species is the first to preserve parts of the skull, so it shows that this early Miocene-aged genus had a slenderer beak than those of living albatrosses. This is likely an adaptation to a more fish-heavy diet. New dolphin bones, baby! Xenophis is a genus of ancient bizarre-toothed whale, first named in 1923 based on a mostly complete juvenile skull discovered sometime around 1900 in the Oligocene-aged Ashley Formation of South Carolina. Exactly a century later, Robert Bosnecker and Jonathan Geisler published what I would call a monograph on everything Xenophis in November of 2023 in the journal Diversity. Thanks to the discovery of several specimens of the genus, both within recent years and some discovered a while ago but that had gone undescribed, the team was able to fully describe and amend the diagnoses of the original Xenophis species, Xenophis sloanii, and then also found that a handful of specimens from a geologic formation above that which revealed the original species' fossils contained enough unique traits to justify a new species. They named the new species Xenophis simplicidens. These animals were like rather bizarre, long-snouted dolphins with echolocation that were unrelated to many of the modern dolphin lineages, meaning convergent evolution was afoot. The new remains showed that these animals were adept hunters, with large curved teeth for sinking into fish, mammal, or reptile, and thickened back teeth for slicing up that prey to ribbons for better swallowing. The new specimens showed that the family group to which Xenophis belongs is a true evolutionary grouping of bizarre-toothed whales from the waters around the southeastern US during the Oligocene. Sir, 2 more dome heads have hit late Cretaceous North America. Pachycephalosaurs, the dome-headed dinosaurs, have one of the worst fossil records of all dinosaur groups. This could be for a whole bunch of reasons. One is that they thrived in environments not suitable for fossil preservation, like mountains or rainforests. Another is that maybe their skeletons were just not great at preserving in the fossil record. Though considering their bone structure wasn't much different from their ceratopsian cousins, this doesn't seem likely. Whatever the reason is, their fossil record is made up mostly of these super dense, thickened bony bosses that capped their noggins. Obviously, enough skeletal material has been found globally to get an idea of what these animals looked like, but the majority of stuff being described these days are just the domes. To that end, a pair of dome specimens, one from the Dinosaur Park Formation of Alberta and the other from the Hell Creek Formation of Montana, were described in November of 2023 by Kerry Woodruff, Ryan Schott, and David Evans in the journal Papers in Paleontology. These two specimens contained enough anatomical traits to convince the authors that they represent two new species of the genus Spherothalus. For context, Spherothalus is one of the most speciose genera of dinosaurs, with 3 known species before this new publication. Psittacosaurus is still number 1 though, with 10 valid and 19 possible species. The authors named the Albertan specimen Spherothalus triregnum, and the Montana species Spherothalus leesoni. Both of these new species are each other's closest relatives and prove that these animals continued to diversify quite readily throughout the end of the late Cretaceous. Another pick-handed freak. The more birdy the dinosaur, the crappier the remains tend to be. This is not because birdie bones aren't strong, but more so because the hollowness lends the bones to being slowly broken down and disintegrated by natural processes. However, special circumstances allow these sorts of skeletons to be preserved in fairly good detail. One of the many bird-like non-bird dinosaur lineages is the incredibly bizarre Alvarezsaurs. These small theropod dinosaurs are most well known for the adaptation of a highly reduced forearm, ending in usually just one big clawed finger. The earliest forms of these dinosaurs had more normal hands, and then the latest ones just had one big clawed fingy. Most of these dinosaurs are known from bits and pieces, with only some having good to great fossils. One of the best so far was a late Cretaceous Mongolian form described as Jaculinicus yarui by a team of Mongolian scientists in +1. This specimen is pretty much the entire skeleton and shows a small, wispy animal with a toothless, pointy snout for licking up small prey, and only one extra vestigial digit next to the giant claw on its hand. The authors think the specimen was sleeping when it died, as the head and neck were folded over the arm and behind the leg, as seen in some birds today. Poor thing. Did Thescelosaurus dig? Thescelosaurus was a cow-sized genus of bipedal ornithischian dinosaur that thrived throughout late Cretaceous North America. There are currently 5 valid species known to science, with many dozens of specimens. Therefore, they are great critters to use as experimental subjects to understand the internal soft anatomy and behavior of this side of the ornithischian tree. To that end, David Button and Lindsay Zano CT scanned the skulls of Thescelosaurus specimens to recreate the brain to get an idea of how smart these things were, and what they were doing with those smarts or lack thereof. They published their work in November of 2023 in the journal Scientific Reports. They found that Thescelosaurs were not quite problem solvers. Intelligence is hard to quantify or even qualify in extinct animals with no direct living analog because a small brain may not inherently mean the animal was dumb. Even here, some animals you may consider dumb are still capable of complex social behaviors. Just look at crocodiles. Anyways, the Thescelosaurus brains inferred they had a narrow hearing range, but a super strong sense of smell and balance. The authors used these traits and those of the skeleton, mainly the robust forearms, to hypothesize that Thescelosaurs were good at burrowing. However, their large size meant they probably weren't subterranean specialists or anything, just that they could burrow, and they had the internal anatomy for burrowing. And that was the gist of November of 2023 in paleontology. Unfortunately, whoever was doing November for 2023 was unable to complete it, so I stepped in quite late. Next up is also me for December of 2023, so stay tuned for more me. New fossil condor. Condors are New World vultures with broad wings and short tails. The fossil record of condors in South America is scarce, and particularly in Argentina, most of the remains assigned to condors have been debated. a team of researchers described fossil remains of a new species of condor from the early Pliocene Catamarca province, Argentina, that belongs to the still-living genus Vulture. The new species, Vulture messii, is considered to be the only valid fossil species of this iconic genus of birds. The presence of a fossil vulture species, recovered from deposits older than 4.8 million years ago, coincides with the rise of the Pompeian Hills and the Andes, and the beginning of the regional aridification. The existence of incipient mountain chains may also indicate that the center of origin of this genus is linked to the Andes mountain, which in turn indicates an earlier arrival and diversification of the condors in South America than previously realized. Teenage tyrannosaurs loved held chicken drumsticks. Tyrannosaurids were enormous carnivorous dinosaurs whose skull robustness and body proportions changed dramatically as they developed, indicating that they inhabited diverse ecological niches throughout their lives. Although adults ate mega-herbivores, the diet of juvenile tyrannosaurids is unclear. A team of researchers reported a unique juvenile Gorgosaurus specimen that has the articulated hind limbs of 2 yearling Oviraptorosaurs in its gut. In 2 independent feeding episodes, the prey were selectively dissected and devoured. This predator-prey connection demonstrates an ontogenetic dietary shift in tyrannosaurids. Juveniles may have hunted tiny immature dinosaurs until they reached a size where they needed more energy and switched to eating mega-herbivores. Tyrannosaurids fulfilled both mesopredator and apex predator roles throughout their lives, which may have been critical to their evolutionary success. Another killer land croc from Valley of the Crocs. Bonusmousai is a group of Notosuchian crocodiliforms ubiquitous to South American Upper Cretaceous deposits. They are distinguished by having dog-like skulls, reduced tooth rows, and enormous canine-like fangs. A team of Brazilian paleontologists described a new species of a previously known genus of these non-crocodilian crocs from the Adamantina Formation of southeast Brazil. The new critter is composed of a right portion of the skull, cranial roof elements, fragments of the secondary palate and the lower jaw, as well as 6 isolated teeth. They decided to name the new species Aphaurosaucus kaiju. When they inserted the new critter into the phylogenetic framework of their chosen software, they found the new species to belong to the same family as the previously named species, Bonusmousai. No shock there. But adding in the new croc as well as a few others rearranged some other crocs. They found that Ogresaucus and Rosinandragobe were non-Bonusmousai Bonusmousaians. This means that the inclusion of these 2 crocs in an otherwise well-established Bonusmousai clade suggests that these animals had a much broader spatial and temporal distribution than initially thought. Cretaceous blind snake fills in major snake gap. Blind snakes are minute, cryptic snakes that diverged at the base of the evolutionary radiation of modern snakes. They have a scant fossil record, which dates back to the Upper Paleocene to Lower Eocene, about 56 million years ago. This late appearance conflicts with molecular evidence, which suggests a much older origin for the group all the way back to the Mesozoic, around 160 to 125 million years ago. In December of 2023, a team of researchers described a new typhlopoid blind snake from the late Cretaceous of Brazil as Boepeba tiasuensis. This new critter extends the Scolicophidian fossil record into the Mesozoic and reduces the fossil gap predicted by molecular data. The new species is estimated to have been over 1 meter long, much larger than typical modern Scolicophidians, which are usually smaller than 30 centimeters. This finding sheds light on the early evolution of blind snakes, supports the hypothesis of a Gondwanan origin for the Typhlopoidea, and indicates that early Scolicophidians had large body size, only later undergoing miniaturization.
Megafinned humpbacked mosasaur.
One of the more interesting discoveries published in the month of December was a largely complete skeleton of a mosasaurian mosasaur from the Wakayama prefecture of southwestern Japan in the Hasegawa Muddy Sandstone member of the Toyajo Formation, making it about 72 million years old. The new critter is represented by many skeletal elements, including the skull, a complete neck and back vertebral series with more than 40 vertebrae, paired ribs, right and left front flippers, and the left hind flipper. The team of researchers named the new creature Megaraptorion wakayamaensis, with the genus name meaning big wing, and the species name referring to where it was found. The two sets of large wing-shaped flippers were likely selected for fast maneuvering, as seen in the humpback whale. The presence of a dorsal fin is suggested by the sweeping arrangement of the neural spines along the dorsal vertebrae, well posterior to the presumed center of gravity. The very first humpbacked mosasaur and the very first to actually have some form of direct evidence of the possible presence of a dorsal fin. Mantaworm of Nevada. Lobopodians are an iconic and diverse group of animals from the Cambrian, which, alongside radiodonts, present an important window into the evolution of arthropods and the development of Paleozoic ecosystems. Of these, a rare few species outside of radiodonta possess lateral swimming flaps. The recent discovery of Inoopteris provided much-needed insight into the evolution of swimming flaps, suggesting that the ventrolateral flaps of Carrickmacella evolved independently from other flap-bearing lobopodians and radiodonts. Paleoartist and paleontologist Christian McCall, better known online as Prehistorica, described a new pelagic lobopodian species as Mobulovermis adustus, the first lobopodian to be reported from the Cambrian Age Pioche Shale of Nevada. Mobulovermis was large and possessed more ventrolateral flap pairs than any other known lobopodian or radiodont. It was found to be a close relative of both Carrickmacella and Inoopteris, allowing the establishment of the new lobopodian family Carrickmacellidae. Giant early German snakes. Next up, we have a team of researchers who described two exceptionally preserved fossil snakes from the Eocene Konservat-Lagerstätte of Geiseltal, located in the state of Saxony-Anhalt, Germany. They found these snakes to be boas that were so closely related to the already known genus Eoconstrictor that they were confident in describing them as a new species, Eoconstrictor barnesii. Phylogenetic analysis of snakes consistently supported a close affinity of Eoconstrictor barnesii to Fischeri and Spinifer. The team's preferred phylogenetic hypothesis posits that the three species of Eoconstrictor are in a clade that is sister to the Neotropical Boidae, a result consistent with previous studies. The genus Eoconstrictor could therefore provide an important calibration point for molecular clock studies of boids and snakes in general. Another Chinese unicorn added to the list. The elasmotheres were well-diversified and widespread rhinos throughout the Neogene in Eurasia and East Africa. A brand new one was published this December from the Middle Miocene Zhanghenbao Formation of Tongqing, Ningxia, China. The publication team named the new beast Tongxinotherium laterinum. A phylogenetic analysis revealed that it is more derived than the early elasmotheres and more primitive than Uranotherium and Ningxiatherium, bridging a morphological and stratigraphical gap between them. The discovery of new material improves the morphological characteristics of the early elasmotheres' horns and increases the diversity of the Middle Miocene elasmotheres.